Hello and welcome. Today we're going to do another Lagrange multiplier example problem. So let's do it really quick. We have z is equal to f of x comma y, and that's going to be equal to e to the x times y. And the constraint is going to be x to the third plus y to the third is equal to 16. Okay, and that's going to be g of x comma y right there. All right, so let's sort this one out. As we always do, we have to set up the multiplier equation, which is grad f is equal to lambda grad g. Okay, so grad f is equal to, well, we have to take the derivative of this with respect to x, and we're going to use the chain rule to get that, y times e to the x times y, and the similar equal and opposite, taking the derivative with respect to y, you end up with an x multiplying out in front of e to the x times y. All right, and now we're going to set that equal to lambda times, and then take the derivative of our constraint equation. And so what we have here is the partial derivative of x is going to give us a 3x squared, comma, and then comma 3y squared like that. Okay. All right, so now let's set up the two equations. We're going to have y e to the x times y is equal to lambda 3x squared. And we also have x e to the x times y equals lambda 3y squared. So what we see here is we have to solve this equation. We have to look at those two. Those are the same thing. So if I can make whatever's on this side of the equation the same and equal to e to the x times y, then I can set them equal to each other. So what I have here is a lambda, a 3 lambda, x squared over y is going to equal e to the x times y. Likewise here what we have is we have a 3 lambda times y squared over x is equal to e to the x times y. All right, again, we still don't know what lambda is, but we know that these two, whenever you have these things over here on the left, they're both equal to the same thing on the right. So we can say that 3 lambda x squared over y is equal to 3 lambda y squared over x. So at this point, we can cancel the lambdas for now. Okay, we don't need them. Now, they may still have a very specific value. Lambda might be a very specific number, but we just don't need to know that number right now. So what we have here is x squared over y is equal to y squared over x. Okay? I can move this one around even more, and I get an x cubed. If I multiply both sides by x times y, like this, I get an x cubed is equal to y cubed. So this equation then would suggest that what's really happening here is x is equal to y. All right, so what we have here is this line of points. So x is equal to y, but of course, what we have to do, of course, is we have to find an xy combo that satisfies the original constraint. In this case, it's equal to 16, so it's x cubed plus y cubed is equal to 16. So we have to find the specific number that lies on this curve, this level curve that's defined there. All right, so we know that x is equal to y, so that means anywhere I see a y, I can put an x. So I'm going to get is 2x cubed is equal to 16, and then I get an x cubed is equal to 8 when I divide out the 2, and then finally x has to equal 2, and therefore y has to equal 2. So I found a very specific point, 2, 2. So that's the solution to my problem. We can go back and figure out what lambda is. You don't need to know this, but I think it's good to check to see if just to see that it all makes sense. So what we have here is 3 lambda times 2 squared, which is going to be 4. So what we have here is 12 lambda is equal to 2e to the 4. So what we have here is lambda is equal to e to the 4th over 6. Okay, so that's what the lambda value is in this particular case. Again, you don't need to figure that one out, but I always like to go back and check. There's no other points. Now, all of these points along this line, x is equal to y, they all, you know, but we're looking for only that specific one that lies on this level curve. Okay, so this is a, you know, this is going to be a shape that kind of goes like that as it goes out. So so eventually it's going to, you know, dip down into the negative numbers for x and y. But the idea is we don't need to know about it. We just know that 2 is the answer. So again, to find the final answer, of course, it's going to be z is going to be equal to e to the 4th. All right, because that's e to the x, or 2 times 2 there. So this is our critical point. So I would say this is going to be, clearly it's going to be a minimum, because if I go further out, well, actually, I don't know if it's a minimum. It's a good question whether it's a minimum or a maximum, because our numbers x and y are limited by the fact that they both, when cubed, have to add up to 16. This would seem like it's actually a maximum to me, that critical point there. I'm sure we could figure that out. Let's see if we can figure that out. So we have e to the x times y, and of course we have x cubed plus y cubed is equal to 16. What I can do is say that y is equal to 16 minus x cubed, cube rooted, like that. There is your curve. Remember, this can be negative. Cube roots are defined for negative numbers, so you can plug that in, e to the x times root 3, 16 minus x cubed. So that's really what this function looks like. And of course, if I take x really big, x times y is going to become negative, and that means e to the x times y is going to go small. So it looks like 2 is going to be a local local maximum. Or I shouldn't say a local maximum. It's just going to be a maximum. It's going to be a maximum on the level curve. X cubed plus y cubed is equal to 16. Okay, well, I hope that gives you some insight into how to use Lagrange multipliers to answer these questions. I'll see you in the next video.